We?
Yes.
Go ahead.
Okay. Hello guys. This is Group 8, and we got Will, Unwell, and Khaled, Marat, Boozer, to Marat, and Barry. Okay, next slide. This is our table of contents, and I do some handoffs, and Khaled do some embeddings in clustering, and Marat do the audio processing, and Booster done some GUI integration.
Very good.
And next slide, please. And I'll start from some handoff. Next slide, please. Next slide, please.
You went crazy with the graphics on this.
Yeah.
90% of the effort.
Yeah, I mean,
the graphic design is next level, I have to say. But yeah,
I mean, this is final presentation, so yeah.
Exactly.
And I will start with a quick overview of the data set we're using, so our implementation choice makes sense. So we're using the Freesound Loop Dataset, or so-called FSL 10K, and it's roughly 9K plus loop sample. And each loop comes with the useful metadata like BPM or genre or text, maybe instrumentation, or sometimes key. And that metadata is really important for filtering or clustering and conditioning our generation. The raw file we got are basically two packages. One is the FSL10K.zip and another one is annotation.zip. And since this dataset is large and the folder structure can be annoying across in the environment, so our first priority was to make the data layer stable and consistent before building embeddings or generation or the GUI. Okay, next slide, please. And here are some the risks and the speed part. And this slide is basically the motivation. Is that the biggest hidden risk is not the model itself, is that everyone parsing the data differently. So if one person read the metadata one way and another assumes a different audio path, and someone else handles text differently, the integration becomes a mess. So we decided early to enforce a single source of the truth. This kind of approach is that one consistent data interface that everyone uses. So that way we reduce the integration risk and also speed up for everyone, because nobody has to waste time on setup and debugging file path. Okay, next slide, please. So I did three things here at high level. I standardized how we access the data set, the audio metadata, and the annotations. So it works it works in the collab and doesn't break due to small folder structure differences. I built a clean master index key by sound ID, so the metadata and the actual wave files are aligned in one place. And then I packaged everything into the handoff artifact, so other groupmates can work in parallel immediately instead of wasting time redoing the data preps separately. So in short, I turned the raw data set into something, I would say, engineering friendly, so the rest of the pipeline can build on. Okay, next slide, please. To make sure that integration is smooth, we set a simple, maybe I would say team contract. Is that the only entry point is that index.csv. The only unique key is a sound ID, and always load the audio using the wave path, and no hard-coded folder assumption. So this keeps Calypso embeddings and Mirage generations and boosters GUI all align with the same IDs and the same data format. Next slide, please. Finally, here are some I would say here's how this helps the rest of the team. So the Halid can directly compute the embedding from the wave file using the wave path and write a result back using the sound ID. And Mirage can do sampling in embedding space and then do approximate decoding like KNN or something like that, while still being able to trace everything back through the sound ID. And Booster could build a GUI on top of the index.csv for the browsing or filtering or playing loops, and then call Mirage generator for the output. So overall, I reduce the biggest integration risk early so that we can move faster and avoid the last minute failures. And
Excellent.
that's for my part. Next, Halib will cover the embeddings and clustering slide.
Yep. So next slide, please. My goal was to translate raw audio into something our AI models could actually understand. So first I wanted to choose OpenL3, but it basically didn't work on Windows without really big problems. So I chose PAN's CNN14 because it was pre-trained on Google's audio set, really massive data set, and I specifically picked CNN14 because it was a balance between really fast computerization and good mm, good results.
When was the model released? When was this model released?
Oh, I'm honestly not sure, but I think it's pretty old because I saw a lot of another transformers, and
Yeah, exactly.
I'm sure they will give better results. But I
Of course.
chose this for more speed, maybe. Yeah.
Yeah, of course, of course, of course. And you said that this is a Google model, or who trained it?
It was trained on Google and by Google. Yeah.
Okay, okay, go ahead.
So next slide, please. Yeah, and to handle these 10,000 files, I did fast inference pipeline. It analyzes only first 3 seconds of each loop.
I see.
So to capture the core style, and it saves hours of compute time. For example, for these 10,000 files, it takes around 20 to 30 minutes now. And then I used UMap to squash the data into 2D map and k-means clustering to automatically label the sounds. And as the graph shows, the model successfully found distinct musical groups, and also it took together broader categories like general electronic sounds like BPM, you can see.
But these are embeddings, right? These are still music embeddings, right?
Yeah. And
Okay.
this is final time manifold. You can see islands where similar instruments group together, proving that CNN14 actually works. Also, I validated the results mathematically, and so I had an R square score of 0.21. So it validates high encoding of both timbre and rhythm. And my handoffs were delivered to another my teammates for tasks 3 and 4, I believe, like .npi for math and .csv with coordinates on UMap and another features.
Okay, excellent.
Okay, so now I'm going to talk about my part, which is audio processing. Next slide, please. So this figure illustrates the overall generation of the pipeline of our system. Like at first the latest vectors, then it translates into, and it choose some audios, and then we slice it, and then we generate a new loop. So we have a final loop. Next slide. So here is some models that how we choose the loops we wanted to combine. So like on the left, we have the single Gaussian model. So we assume that all embeddings within a cluster can be approximated by a single distribution. So sampling from the model produces one vectors near the global means of a cluster. So as a result, the generated loops tend to be like more stable, but they are often lack diversity. So in the middle, we show the Gaussian mixture model, it's GMM. So rather than assuming a single model, GMM represents the cluster as a weighted combination of multiple Gaussian components. So each component captures maybe some sub-style of rhythm pattern within the cluster. Then on the right, we have a kernel density estimation, which is KDE. So it's a fully non-parametric approach. And so instead of fitting a predefined distribution, KDE places a kernel around each data point and estimates the density direct from the data. So the sample length vectors are closely follow the actual shape of the embeddings distribution. So this makes KDE tends to generate land points that are similar to the loops we wanted, that we choose. Next slide.
Yeah, this one here, I would say that you go from the simplest model to the most complex model, right? So
yep.
they're all inside each other. Go ahead.
Yep. So here in this stage, the model is responsible for selecting loops that are stylistically similar and suitable for recommendation. So like we said, we sample the landing point from the cluster we can use 3 different types of models like Gaussian, GMN, or KDE. You can choose it. So this sampled vector represents a desired position in the embedding space. So as a result, the select loops share similar rhythm and some characteristics. So even though they may come from different original audio files. Next slide, please. So then once the source loop are selected, we perform some editings to construct a coherent output loop. So first, we decide a target tempo. So in our code, the users can choose a BPM. And next, we define a fixed time grid based on this BPM. Like 1 bar is converted into an exact number of samples, and then evenly divided into K segments. So the concatenation, all segments always produce exactly 1 bar. So it can perform a loop. So we then tempo normalize each select loops. So using time stretching. And then after that, we extract segments in a structured way. Like instead of random slicing, each loop contributes a different segment offsets, which introduces variations while preserving the overall rhythmic structure. So to improve precursor quality, we apply short crossfades that segment boundaries. So this smooths some transitions and reduces clicks or some abrupt changes in the loops. Yeah, so finally we concatenate the segments into a seamless loop. So I adjust it to exact bar length, then repeat it to form a usable multi-bar output. Okay, so next, Buster will talk about the graphical use interface and the demos.
Right, so let me just set it up real quick. As I thought, I'm responsible for the GUI, which I will probably pronounce as GUI. That's I don't know why, but that's how I pronounce it the entire time I've been working with it. So that's what I'm gonna do. I thought it would be simpler it would be simpler to just show it as it is web-based. So I could just change my my tab if I remember how to do it. So you should be seeing a GUI instead right now. So yes, this is the GUI for our audio generation function. It can sort by the different clusters that you want. You can also apply a certain BPM range to find through this one magical data table known as index.csv, which I used to which is just showed here. Can also apply a volume, which is probably a pretty nice thing to do because it's going to be loud. And search by something weird like electronic or something. Then you click on the files here. You can listen to them here. Pick something that's probably in the same cluster and same BPM and same tags, and you might get a consistent result. If you want to deselect files, you can click on them again. Or if you can't find them, then I added a just deselect them all. Then there are all the parameters that Marat talked about, like the model choice, the amount of slices that we do, the crossfade, and then of course a file name. Let's just call it test. Then you click on generate, and if the file already exists, you can overwrite it or not, and then it will take around 10 seconds, 10 to 20 seconds for it to create an audio loop. So that it doesn't take more, because then it would be awkward.
It's like a
20 seconds.
Apple presentation, you know. It's like when the iPhone doesn't pick up the call from Mark Zuckerberg. Go ahead.
Yeah, exactly. And then you can preview the audio, which didn't turn out very good here because I'm also pretty. But you can hear how the audio process works by just listening to it. It's very. You can hear that it's just taking and stitching samples together, where you. Sometimes you will get some very abrupt changes. That usually happens if the audio files you choose are not very similar, because then the audio files that the model chooses will also be different in many ways, and you get stuff which are not quite the same. Where you just completely.
Wait. I'm just confused about this step, right? Because. So where is the actual sampling of the kernel? Where is the sampling taking place? So now you have 3 samples selected, right?
Yeah.
Then you should look at the embedding.
Yeah.
You get the embedding space. Then you do KDE over the embedding space.
Yeah.
Then you how many samples do you sample from this embedding space?
That Marat would be able to answer that. I have just gotten the Python function and gotten it to work.
Just explain to me, right? So
yeah.
Then you do the KDE over the embedding space, right?
Yeah.
Yep.
And then you sample from there. How many samples do you pick out from the sampling space? Just one?
From the slides, you can see that if it's 3, then we'll try finding 3 loops that are similar to the loops you wanted. Yep.
So when you do the sampling, you're just sampling existing loops in that space. Is that correct?
Yep. Yes.
Yes. Because in my mind, I would have preferred that you create new samples, right? And then you invert back the new samples in the original space. I understand. Because this embedding, do you know if this embedding is invertible? It's not invertible, right?
Yep.
Okay, good. Okay, good.
Yep.
Okay, very nice. Thank you, guys. Any questions? Okay, very good. Okay, go ahead, guys. Group B. Is there a group B? Group B.
Yeah.
Here we go.
Hello everyone, we are Group B, and our project is random loop generation from clustered audio loops, and I'm responsible for dataset to make the dataset friendly preprocessing for my teammates. And our problem statement and goal is to generate a novel audio loop that matches a target style of random cluster. The input is 2 to 5 user selected loops, and the output is a new loop that is consistently in style, timbre, rhythm with the implied cluster. A key constraint is that the output must be listenable and also loop friendly, meaning the boundary should be seamless without obvious clicks or hops. And our dataset is FSLD dataset, provides wave loops and metadata such as tempo, BPM, key, and instrument tags for engineering reliability. My job is to build an internal index that maps audio paths to parsed metadata and text and standardize the data format so that downstream clustering and generation models can consume consistent input. And for data parsing and converge, in practice, the dataset includes a large collection of wave files, but only a subset has usable annotations. After parsing, we counted the total wave files, the number of annotation JSON files, and the number of loops that successfully match an intonation. To make matching work, we implemented sound ID normalization because audio file names and intonation IDs may follow different naming patterns. This step is critical, and if the pipeline would appear to have no tag, which breaks conditional sampling and debugging. And our EDA tag distribution, we perform EDA on the tags. The distribution is long-tailed. A small number of tags appear frequently, such as loop 120 BPM and ambient, which most tags are rare. This plot is useful for two reasons. First, it helps us quickly sanity check metadata parsing. No empty text mean parsing works. Second, it provides a practical signal for cluster-like sampling and for debug pipeline behavior before heavier modeling. And our loop-friendly audio spec is we standardize audio by resampling, normalizing, and trimming to a fixed duration. We also reduce boundary artifacts by removing head or tail silence or noise edge. We apply crossfade at the boundaries to reduce clicks and support seamless looping. To iterate efficiently, we design two models. First model use lower sample rate and shorter clips on a smaller subset, while high quality model use high sample rate, longer duration, and a larger data set. And this is our pipeline overview made by...
Question. So for the fixed duration, that's a function of the BPM, I guess, right?
Yeah.
Yeah, okay.
And this is
So,
the pipeline.
So what's the duration? Like 3 seconds, 5 seconds, 4 seconds? What's the duration?
For fast model, it's
okay, 2 seconds. Okay, go.
Yeah.
So 2 seconds plus or minus whatever you need for the BPM in order to remain a loop, correct?
Yeah.
I don't know if you say yeah, or I mean, I don't know if you're just automatically saying yeah, or if it's really, you understand what I'm saying. Go ahead. Yeah.
Okay.
Go ahead.
And our integration and reproducibility to make the project usable for the whole team and provide a single callable API, one entry point that runs the full workflow from load, preprocess, model, export. For reproducibility, we use fixed random seed, standardized folder structure, and consistent file paths. So in a clean environment, anyone can follow the README, run the same pipeline, and then reproduce outputs reliably. And our output example is output wave. After generation, we apply post-preprocessing such as normalization and boundary smoothing to improve loop playback quality. In quick listening check, the crossfade-based boundary handling noticeably reduce clicks or pops at the loop point. And then we create 10 demo pack loops to from loop 0 to loop 9. These are exported in a consistent format and stored under the loops folder. And for the limitation, there are several limitations. First, annotation coverage is partial, which limits conditioning quality and reduce controllability. Second, even with crossfade, we don't guarantee perfect bit or alignment, so rhythmic phase might drift across the loop boundary. Third, evaluation is most qualitative listening, and we lack a strong object metric for loop quality. That's all for my part. And next to our second teammate.
Okay. You're gonna tell me how you did the embeddings and the sampling. Go ahead.
Okay. Next up is my part. So the goal of my part is to turn each audio loop into a vector embedding so that similar loops are closed in the embedding space. If the space is meaningful, we should be able to see structure with visualization and verify it with simple probe tasks. And the final outputs are an embedding extractor, an analysis notebook, a scatter plot, and a CSV file containing probe metrics. Okay, next page. And okay, so the core problem is, can we build an embedding space that supports clustering and interpolation for audio loops? And our acceptance criteria is practical. We don't need perfect labels, but we need evidence that the embeddings are not random. So I validate the space in two ways. First, a 2D visualization like UMap, where we color points using available annotations. And second, a small sanity check, models that predicts tempo bins or common text from the embedding. Okay, next page. And the data set contains around 9.5K audio loops, and I aligned audio files to metadata successfully. There's 9,486 audio files were matched. For labels, the main structured annotation we have is tempo in ANN.bpm. We don't have clean genre, key, or instrument labels in the metadata. And to still evaluate structure beyond tempo, I also use tags as weak labels and create a top tag classification probe. This gives a second signal of whether embeddings capture timbral or content information. Okay, next page. And so for the embedding method, I followed pre-trained first approach. I use Hubert based from Torch audio.pipelines to extract a 768-dimensional embedding per clip.
Yeah, because Hubert is usually more for speech than for sound, right? So I wonder who is the performance. Like Hubert is mostly, I know Hubert only for speech, right? Is also Hubert is also trained for sound, for music.
I think speech is also a part of a sound, I guess. So
yeah, but it doesn't generalize, right? So because Hubert, you use it for example, speech to text, right? So you cannot think that a speech to text model will do well into a music context, right?
Maybe I didn't think that much through, so I just picked one and maybe okay.
Yeah, I think you might have picked the wrong one. Let's see how it goes. Let's see how it goes. No, I mean just because. Yeah, go ahead.
Okay. And processing is simple and consistent. Convert to mono. We sample to 16,000 Hertz. Peak normalize and trim to a fixed window for compute control. And because I'm running on CPU, I tested different clip lengths, 2 seconds for last iteration and 8 seconds to better capture tempo cues. And for pooling, I mean pool features over time from the last layer to obtain 1 vectors per loop. Okay, next page. And here is the UMap visualization of the embedding space. So each point is 1 loop embedding, and I color points by tempo bins derived from AN.BPM.
Just a second. So here you so the BPN, because sorry. Okay. So colors that belong to the same BPM, same BPM means the same color, right? So you should see a clustering of the points according to the BPM, correct?
Yeah.
So you don't show, you don't see any grouping, correct?
Yeah, no obvious.
So you saw the mapping, you saw the clustering that the previous group had, right? That the cluster according to the genre, right?
Mm.
So your grouping fails. So your embedding is not preserving the clustering. Right? Correct? It's completely random, right? There is no pattern.
No obvious pattern.
I wouldn't say also, so not obvious. Okay, go ahead. Yeah, okay. I think you took the wrong embedding. I think you just took the wrong embedding. Go ahead.
Okay. So we see here is partial structure. So certain regions have more concentration of similar tempos,
Don't tell me that. Don't tell me
still
that. Just
significant
uniform.
mixing.
It's just uniform. Don't worry. There's no pattern. Go ahead.
So
go ahead. This is just random.
Okay. So next page. So to quantify the clustering tendency, I ran k-means and computed 2 metrics. The Still score is about 0.068, which indicates weak cluster separation. And I also computed NMI between tempo bins and cluster assignments around 0.063. So suggesting that tempo only partially explain the clusters.
Of course. Go ahead.
Okay, next page. And so next I ran probe tags using simple linear models on top of embeddings. So for example, direct regression is unstable in this setting. And although MAE improves to around 27, this suggests tempo prediction needs better temporal modeling or pooling. And so for classification probes, results are more stable. Top tag classification reaches about 0.3 accuracy and 0.268 macro F1, indicating embedding contain usable information related to common tags. And for tempo, instead of regression, I also do tempo bin classification with mixed bins, and the macro F1 is lower due to severe class imbalance.
So, but there, when you do the classification, you do binary classification, or you bin the tempo. What type of classification you do there?
Tempo bin classification.
Yeah. So how big is a bin?
Okay.
How big is a bin? Yeah. Like 0 to 10, 10 to 20.
Because the class imbalance, so I switched to quantile bins. The quantile bins is Q equals to 5. I get about 0.367 accuracy and 0.298 macro F1.
I mean, just complete disaster, right? So go ahead.
Okay. So next page. So I think I did so wrong, so I'll just probably skip this part. Okay, thank you.
Okay, go ahead. Guys, I cannot hear anything. Guys, what is happening?
Oh, yeah, he opened his mic. Okay.
We have a broken microphone or a fleeing student. One of the two. Sorry. Okay. Still don't know what's the issue. Guys, what should we do, guys?
He text a message in our line group.
Wait.
And we check the situation. Oh,
we can hear you now. We can hear you. Go ahead.
Okay. So, this is my part, and I successfully processed and sequenced 9,485 FSLD records, achieving a 99% match rate between the metadata and raw audio files to maintain consistency for future extraction. I implemented an automated workflow that uniformly converted all audio to 16,000 Hz mono 16B PCM. I also integrated automated silence streaming and open to normalization. And okay, next page. So once the data was ready, I performed a robustness analysis to validate our latent space. To test this, I injected random Gaussian noise into the original audio to stimulate real-world environment interference. The results were outstanding. We achieved a mean cosine similarity of 0.9412.
Yeah, this makes sense. Now, let me tell you. So this makes sense because the embedding is wrong, but the embedding is trying to reject environmental noise. So this makes sense. This makes sense to me. Go ahead.
Okay. And this high score provide that our Hilbert-based embedding space is extremely stable. It gives us the scientific confidence that small perturbations of noise will not cause significant semantic shifts, ensuring our AI remains focused on the core musical features. Okay, next page. And the major challenge in test 2 was proving invertibility. Basically, we can turn these abstract vectors back into sound. I developed an audio decoder using KNN retrieval mechanism. As you can see from the waveform comparison on the slide, there is a very high visual correlation between the original and the reconstructed signals. We successfully mapped 760 dimensional vectors back to high fidelity audio. This proves that our latent space isn't just a bunch of numbers, it efficiently captures the acoustic sound of the musical loop. And next page. In music production, the difference between a good loop and a professional loop is how we handle the thing. Raw audio cuts often suffer from clips and pops due to phase discontinuities at the start and end points. To solve this, I implemented a 5% linear crossfade algorithm by applying a 0.05 second fade in and fade out. We ensure that the transitions are mathematically smooth. The outcome is a collection of seamless loops that can be played repeatedly in any professional workstation without any audible glitch.
Okay.
Next page. To conclude, my rule serves as a bridge and a quality guard for this project. By proving the standardized truth dataset, the robustness metrics to validate our logic, and the audio decoder interface. I commented the feature instructions. Essentially, I ensured that while our AI was doing complex math in the background, the final output remained a professional, high-quality audio project that meets into. Thank you.
Very good. Very good.
And the next part is my part. My goal was to create a generative engine that translates audio into a mathematical latent space and use probabilistic modeling to generate entirely new and unique loops. Okay, so to make generation possible, I first had to define the latent space since raw audio is too complex to model directly. Therefore, I compress each loop into a compact 20-dimensional vector. The process had two steps. First, we extract features frame by frame, which means we use 13 MFCCs for the time period, which means the tone color, and 7 spectral contrast value for the texture. Crucially, the second step is compression. Since every loop has a different length, I calculated the global mean of these features across time. This mean pooling technique collapses the time dimension entirely. It condenses the complex moving wave into a single static 20-dimensional vector. This vector is the robust DNA that allows our model to compare and generate sounds mathematically. Next page, please. And the next step is the core logic of this model. Because we don't want to just copy existing loops, nor do we want random noise. To reach this, we use KDE, which means kernel density estimation. Look at the graph. The red X are the specific loops the user liked. To create variations, I applied Gaussian kernels, which represented by the gray dashed lines to each point. When combined, they form the blue curve, which represents a probability landscape. My generator samples from this blue curve, ensuring every new output is statistically similar to the inputs, but mathematically unique. Next page, please. Next page. Yeah. So now I'm showing the visual proof of that the probability curve actually worked using PCA dimensionality reduction. The red X are the loops the user asked for. In this test, I randomly pick 5 sounds as test inputs, and the blue dots are the new loops my model generated. Notice that the blue dots are tightly clustered around the red dots. This is crucial.
Are they the same or not? Are they the same or not? They look like the same, right?
No, but because they are highly overlapped, so they are actually different. Okay. This because it means we aren't just generating the noise. It has successfully learned the specific vibe of the input and it's generating variations within the exact style.
And so, is this in the embedding space or in the original space?
Sorry, can you use?
Is this in the embedding space or in the original space? This is in the embedding space, right? Those PCA components here are over the original or over the embedding space?
Original. I think it's over the embedding space because I use the data from the previous person. Yeah.
Good.
Okay, so next page, please. Okay, so let's zoom in front of the cluster to a single loop. This heat map compares the DNA of the real loop versus a generated loop. The colors represent the intensity of different sonic features like timbre and brightness. As you can see, the hot spots and cool spots are in the same places, which means the structural patterns match perfectly. This ensures the sound is coherent. However, the exact numerical values are slightly different, which is what gives the generated loop its own unique character. Next page, please. Next page, please. Thank you. Okay, so in conclusion of my part, this model takes the user selection and calculates a continuous mathematical space. This allows us to not only generate new random samples, but also to morph between different sounds. Furthermore, all we need to make these 20-dimensional vectors generated by my model to be actually heard, we only need to make it decoded back into wave files. This is the end of my part. Thank you.
Okay, let's see the
final results. Yeah.
Okay, so I responsible for the GUI and demo integration of our project, and I will present the loop remix generator at the end. So we use the Freesound Loop Dataset, which contains 9,455 loopable audio samples. However, the full dataset output is about 8.8 gigabytes, so it's making it impractical for full download in demo-oriented environments such as OLAP. And next slide, please. To address the dataset size issue, we implement an essential data handling strategy. Instead of downloading the entire dataset, the system selectively extracts a small subset of loops directly from the compressed bucket. This enables fast, stable, and reproducible GUI demonstrations. And next slide, please. In the system pipeline, users select 2 to 5 input loops, and the system generates a new loop through remixing and splicing, and applies post processing to ensure seamless readability in the output. And next slide, please. So finally, we provide a GUI built with collab and radio, allowing users to generate single or multiple loops interactively. The system emphasizes demo readiness, reproducibility, and practical usability, making it suitable for interactive music creation demonstrations. And now we are going to share our GUI.
Very nice. Oh, we are waiting with bated breath into the GUI yet.
Kevin.
Yep. Yep. Nobody says yep.
Okay. So, and I write my part early, so I didn't use the result of our teammates. So it's kind of simple. Okay. So generate. Yeah, and I run a cell that can save our result. So the generate loop can be used as input for further generation, enabling interactive typing. Yes. So we can create some new sounds and make save it in a
Right, but how do you do the generation here? I'm still confused. Because the invertibility is only it's using nearest neighbor, right? So how do you do the after you generate if you generate the new sample of the embedding space? How do you generate the loop back?
We choose some loop from the data set that's selected with. We download. We can download it from the. Yes, we download it in a file of collab.
Yeah,
and
I understand.
Yes, and
then
and
you sample it. Yeah, go ahead. Scroll down.
Yes.
Scroll down. Yeah, go ahead.
Yes, and we can choose the sound we want, like loop 1, loop 2, and loop 3, and choose it, and we press generate, and it will generate the mix of it.
But yeah, but how do you? Let me see the generation part. How do you do the generation?
You mean the code?
Yeah. Random seed, load audio. Yeah. Fade in, fade out. It's okay. Where is the generation? Where is the actual generation? Remix generate. Load audio, stack, shape, time stretch. Yeah. So go down, and you're mixing chunks. Then you mix up the chunks, right? Mix and splice. Go down. Crossfade. But so there is no KDE, there is no embedding, there is nothing, right? When you do the generation one, right? Is that correct? There is
Yes,
no.
I think there's no that, and so I think we have to use our teammates' part, and if there's if it can download the sound and then put it inside this UI.
Yeah. So the generation part is still not there, correct?
Yes, I think not very. I think we're just adding it together.
Okay. Very good. I got you guys. Okay, let's go for group C.
Hello, can you hear me?
Yep.
Yeah, I'm the only one here today. So the rest of the group isn't here, unfortunately.
What happened to them?
I think they were aware that there was a presentation for today, but
I brought it last week and I brought it also yesterday.
Yeah, but they only knew about it yesterday after the broadcasting. But we did have a YouTube video for it.
Okay.
And I also can share my own part. So
Go ahead.
so it should be fine. Okay, so can you see my screen?
Let's see.
Okay.
Okay, you can see your group. Yeah.
Oops. Okay.
Hello everyone, today we're going to present our final project, the Loop Generation System. Our goal is to build an interactive system that allows users to generate new rhythm loops by exploring variation around existing examples. And here's our teammates. Large rhythm loop datasets are widely available, but they are difficult to exploit creativity. Manual remix usually requires experience and time, so our goal is to provide an interactive and controllable way to generate new rhythm loops. And the system takes exact rhythm as an input, exact features and embedding, performing a sample or interpolation in the embedding space, and finally generates new audio loops through an interactive GUI. So we start from the row WAV rhythm loops. During the preprocessing, we normalize the audio and organize all loops into a structural table contains IDs, file, paths, and metadata such as BPM and also some text. And these steps prepare the data so that it can be efficiently analyzed and used for later generation. And each audio loop is represented as a numerical embedding. We use 74 handcraft audio features, which already shown strong performance. And the embedding quality is evaluated using the clustering matrix, dimensional efficiency, and classification accuracy. And the results show clear clustering, high variance explained by the first two principal components, and strong predictive performance. And this indicates that the embedding efficiency captures musical's semantic.
Okay, so I'll pause the video. I have my own slides also. So just give me a moment.
So how did you generate the 74 features? How did you generate them?
I am not sure, unfortunately. That's on my teammate's side, which I can't really answer for their part. Yeah.
Okay.
I only have my own part. So let me present. Okay, so yeah, so I'll be doing task 2. Okay, table of contents as shown.
Good.
So okay, so task 2, we have a few requirements. Basically, we want to have like we need to encode them to basically latent embeddings, and the main target is such that we can have the embedded space is well behaved, so it can be used for generative tasks in task 3 and task 4. One of the things that we want to do here is to have decoding features as well, so we can actually reconstruct the audio from just the embedding data that we have. We need to have semantic preservation, which basically means that if they have similar sounds, they should have similar embeddings. Yeah, if it's different, then it doesn't help in the generation. And also we need to have some augmentation. So, but the augmentation should basically be invariant in the sense that they should be as close as possible to originals without basically the feature should be similar to the originals without changing a lot of the embedding space.
Let me help you there. Let me help you there. Augmentation means that you can make the loop longer or shorter, increase the volume, decrease the volume, do a phase shift. For all this transformation, the embedding shouldn't change much. Go ahead.
Yes. And then after that, lastly is to have smooth latent space, which is to basically enable interpolation between sounds. Yeah. So this is the architectural overview for the task 2. So we have the raw audio, and then transfer it to the 2D space, which is the MEL spectrogram.
I'll stop you there. So the input dimension, what's the input dimension? How many samples? What's the sampling rate? What's the time duration?
If I'm, let me check my data over here. If I'm not wrong, the data is 4 seconds. Sampling rate will be at 22 kilohertz.
Okay.
Wait, let me see. The raw audio contains 88,200 samples each. The MEL spectrogram will be 128 by 173.
And you zip everything down to 64. 64 is very small, right?
Yeah, but 64, I think is the reason why, at least from what I see, is we choose 64 is because it's small enough such that it won't affect. Like if it's too big, it's hard to train the data. But
no, I understand.
Yeah, but it's big enough to make an impact. Yeah. So
yeah, tough challenge. Yeah, let's see. Go ahead. Let's see what happens.
And then also we have like basically the CNN will have 4 layers. They'll be using as such, and the parameters will be around 4 million. So the problem with standard encoders is we actually have the focus. Our main focus is we need to make sure that the embedding space is well behaved, right? But standard auto encoders only ensure that they are optimizing for the space. You can see through the formula. It actually doesn't guarantee semantic structure in the latent space. And what this means is that if you use a standard autoencoder in this project only, what happens will be 2 similar sounding loops may actually be very far apart, and that kind of ruins the purpose of the embedded space. Yeah, and like augmented version may also scatter randomly. Yeah, and oops, the last one is supposed to be blank space. It didn't remove that. Yeah.
Yeah, so
Okay,
you also write in Latin in your free time? Go back.
Yeah, I read a lot.
Sed erat non porus fermentum voluptat, nulla accusam dictum leo, quis equam nib laboris eo. So because I studied Latin for 5 years in high school, right? So I see that we both still enjoy reading in Latin. Go ahead.
Yes, yes. Okay, so afterwards we have this constructive learning. Basically the core idea is we need to do the learning by comparison. So what it does is that instead of using absolute representation, we focus on relative distance between two nodes, two embedding space, for example. So ideally, for positive pairs, they should be as close as possible to each other. So this is where we have like the same loop with augmentation. And negative pair, which is like different loops, they should be very far apart. So the analogy for this is sort of like how if you use the standard one, what you'll be doing is you're memorizing every individual pixel to try to identify different faces, versus you look at the big picture and identify face based on like some features that you can see, like maybe the eyes are different, like they have blue eyes or something. Yeah. So why do we use this? Basically is to focus on the target where we need to have where one of our purpose is to have sounds that are similar, should have similar embeddings. So contrastive learning actually enforces this explicitly, and you can see on the right side the difference without and with contrastive. So with this, we have some mathematical formula. So basically, the purpose of it is just to help us with contrastive learning. Basically, it will pull positive closer and it will push negative away. And this is the formula used in this case. Okay, so for data augmentation strategy, we basically want to train the model using augmentation. But we should make sure that the identity of the loop is still there while creating variation. So these are some of the stuff that we have used to create augmentation.
Just a second. Time shift. Okay, good. Yeah, that's what I would expect. Yeah, very good. Go ahead.
Yeah, and after this, we will do how we train our model is through two-phase training. So the first one is to focus on reconstruction to minimize errors and stuff. So it basically learns the basic encoding and decoding of the data, and it establishes the initial latent structure. So for phase 2, it is more focused on fine-tuning. So this is where we use the constructive model, and it kind of refines the latent space structure, and it ensures that our augmentation invariance is positive. And lastly, there will be the lower learning rate. There's a lower learning rate to preserve the reconstruction in the first phase. So this is the phase 1 result. There's basically the observation is that the loss is reduced by a lot, around 90%. Phase 2 results. So from here we have some few
observations. The loss here is the end-to-end loss, or is this the triplet loss? This is
phase 1 MSE loss.
So it's end-to-end. It's after reconstruction.
Yes, it's after reconstruction, but before using the constructive fine-tuning part.
So you're telling me that you start with 88K samples, you trim it down to 64, and you have a 10% MSE loss. So this is MSE over the mass spectrogram? Is this MSE over the wave? This is MSE over what?
Wait, let me see. I'm actually not so sure. Let me check the code.
There are incredible things being said here, guys. I really struggle in believing it. Is it normalized? I cannot be. There's something because it's MSC. So even if data is normalized, still.
It's okay. I'm sorry. I'm not really sure in this. Trying to look into my.
You understand why I'm skeptical, right? You understand
yeah, because it's like 90%. Like as a 90% reduction.
So you're telling me that I have an 88. So you're telling me that I have an 88K wave file, and I can compress it down to 3 bits, to 3 bytes, and I can send the music almost losslessly. That's a statement that you have, right? That's a statement that you have.
But okay, sorry, wait. I think the 64 earlier when I said 64 latent dimensions, right? This is the number of dimensions that we have.
Yeah, exactly. Exactly. So you're telling me take, because this is invertible, right? And the loss, it's between the input audio and the output audio, correct?
Yes.
So you're telling me that you have these thousands of samples, right? So even let's just say that we have 10,000 inputs in the mass spectrogram, right? 100 times 100, it's 10,000. This 10,000 goes down to 64, and it gets re-expanded out to 10,000, and then you look at the loss between the input 10,000 and the output 10,000, correct?
Yes.
And you're telling me that this 64 is the bottleneck in the middle. So if I want to send music, I take the original song, I zip it down to a 64 dimension, and then I send it over the network to people that want to listen music. And you're telling, that's why I talk about compression, right? Because you can see this is a compressed version of the original music. Is that correct?
Yes, it is a compressed version.
So you're telling me that you believe that these 10,000 samples can be compressed down to 64, and this is almost losslessly. It's your statement, right?
Yeah, wait.
It's a little bit fishy. You understand my point. It's a little bit fishy.
Yeah, I'm a bit confused myself right now also. Wait, okay, we start from. I don't think it is. Well, the earlier sample size that I had, I think is inaccurate. I just think that we are taking the data from the MEL spectrogram.
Yeah.
Directly, which is 128 times 173.
10K. I mean,
Yeah,
more than 10K.
and then we,
10K.
yeah, and then we put it to 8x10 output. Basically, if each layer, each conversion layer is sort each convolution layer basically divides the dimension by 2. So if we have 4 layers, it will be, I think, quite a lot, which is like 32.
Correct.
I'm not sure if the MSE now is correct, but I do have a sample of the reconstruction audio later. Yeah.
It just seems, yeah. So it's possible to do compression, and it's possible to very, very hard compression. It's just that this is a 1/100 ratio, right? You're compressing it's a 1%, right? So 100% gets compressed to 1%, and you're telling me that the loss is 10%. So it's a bit hard for me to believe. Go ahead.
Yeah. Okay. So I'll just carry on. So for training phase 2, there are some observations that we have as well. So firstly is that the triplet loss is 0. So basically all the triplet actually satisfies our margin constraint. From here, we can see that the distance positive has actually reduced overall through each epoch. Basically, it reduced from 72 at the start to around 44, which is 38% closer, which is what we want to see because we want positive pairs to be close with each other. And then at the same time, we want negative pair to be further apart, and they didn't change that much, which is around 220 to 250. So this is the training curves as shown. So there's the first part, which we use just doing reconstruction. Afterwards, we have the constructive fine-tuning. And lastly, the third graph just shows when we did the switch. So initially, during the switch, there may be the reconstruction loss may be slightly higher because this is because it's a different model. So it's trying to there's different interests, yeah, and they are trying to basically change it such that it's for the better. So there are also for constructive, we need to validate our results. So firstly, we can see this through the average distance between the original and augmented, they are still pretty close. And then the original with a different track will be quite far, with the loops stay pretty far. And the ratio is around 5 times per separation, which means that in this case our success rate was 100% and it passed. Yeah. So the observation is that the augmented loops are actually much closer compared to random loops.
Very good.
So this is the distance distribution analysis. So firstly, you can see the distance between same augments and augmented ones, which are similar, and different loops. So you can see that they are quite clearly separated apart, as shown through the green and red distributions. And lastly, the constructive quality, basically, since it's all above the same and different line, that dotted line, it means that it's all 100% success rate. So this is the reconstruction quality as shown. You can see here, original is the left side and the reconstruction is the right side. And there are 6 samples for you to take over here. And if you ask me, some of the features are generally there, so it looks quite similar. But I don't think it is what you say. The 10% loss is I think may not be realistic. So maybe there's something wrong with my data on my end. Yeah, but it looks quite similar if you ask me. Okay, so I also.
No, I mean, just to comment, right? Because you see that when the spectrum is sparse, right? Because this is in log scale, right? So when you're close to 0, right? If you normalize everything between 0 and 1, then the area of low volume will have a very small contribution. So that's what contributes to the MSE, right? Because this is not a relative error, this is absolute error. So if you normalize your MER spectrogram, then it's possible that the small entries are 10 to the minus 5. So even if you accumulate 1,000 of them, then you still get to the 10 to the minus. So it is possible, right? It's just that you understand the discussion. Go ahead.
Okay, so here are 3 reconstruction audio. Unfortunately, I don't have the original audio. I would love to compare them now, but this is the 3. So this is the first one. And this is the second one.
Wait, what was this supposed to be?
Sorry?
What was that supposed to be? Like a car running over a squirrel?
Well, over here, you can hear.
Let's hear it again. Let's hear it again. Remember, I'm like a Spotify executive. You're coming to me with an audio compression algorithm. Let's see your pitch deck. Show me.
Okay, so
what was your statement? What was your statement on the compression quality? Come again. What was your statement?
There's room for improvement. Yeah, and this is the third one.
What is this? Aluminium sheets being tossed off a building on top of a busy road. Go ahead.
I'm not sure. So maybe there's more work to be done. It's not an easy task. The final challenge is not an easy task.
So this is your pitch deck, okay? Let me take off my shirt because you made me laugh so hard that my body temperature went up.
Okay, yeah. So after that we have. Okay, so carrying on, moving forward, we have our embedded space structure. So there's some clustering analysis, which actually shows the different clusters, and shows how they are. Like this just shows how they are clustered together.
So sorry, what is the percentage? Come again. Go back. What is the percentage here? What is percentage?
The percentage is just, I think, basically how many percentage of the samples are in the class in the total.
Got it. This is good. Let me see the numbers a second. Okay, very good. Go ahead.
Yeah, and then this is the visualization. One is PCA, and then one is DSNA. So you can see very clearly that the clusters are reasonably separated. So there's a clear pattern. And the TNSNA also shows that like all of them have their neighborhood structure, like they are all within like close proximity to each other. Yep. And also there are no major outliers or collapse regions. And lastly, the overall space is actually well distributed, which is important for generative sampling.
Yeah, it's good.
Yeah, and this is the interpolation of how they generate the thing. Obviously, it's not the best, as you can tell earlier. This is the mathematical formula used for it.
So when you had to, just a second, when you had to do the interpolation, you didn't do a KDE or something. You just use this linear interpolation. Is that correct?
Yeah, I use linear interpolation using the CNN. So I didn't. There wasn't like advanced stuff on it. Which, yeah.
But you understand what I wanted you to do, right? I want you to take a bunch of samples, find the distribution, and then take a samples from that distribution. Did you understand that? That was my
yes.
Okay.
Okay, so in conclusion for task 2, basically we learned that the standard and autoencoders aren't enough for this challenge. They don't actually guarantee semantic structure, and by using constructive learning, it actually helps us basically helps teach similarity relationships to the machine. Yep, and basically two-phase training helps with that also. Where we focus more on reconstruction first, and then we refine it using constructive learning. Lastly, augmentation design is also important because it defines what it shows us what similarity means in audio. And lastly, by using qualitative validation, which isn't that accurate now because the audio was pretty bad, but it actually helps us ensure that it helps us measure our success rate and ratio metrics to ensure that it actually works. Yeah.
Question.
So,
you did a lot of deep learning for this part. Did you do deep learning before? Did you let Copilot help you? How did it go?
I did not do deep learning before, but did learn, like I said, I just have like a rough understanding of it. So it sort of like helped in this case, I guess.
Yeah, because I was trying to avoid you guys doing too much deep learning because you don't. I assume that you wouldn't have the background, at least not from this class. But of course, I understand that with Copilot, you can do most of the job, right? So yeah, but go ahead.
So that's it for my part, and I'll continue playing the video for the rest of the other parts. And I'll skip my portion as well. Okay.
Creative sampling, yes, yeah, good.
And in task 4, we perform the creative sample and interpolation in the embedding space. The interpolation produces smooth transition between the select loops, while random walk and metropolis testing sample introduce more diversity. And user can control the parameters, allow us to balance the similarity and generate the result. And here's the interpolation, and here's the random walk. And finally, here is the metropolis testing.
Question. Did you see this part of the code? Because this is not over the embedding space, right? So it did a random walk over what?
Yeah, I think this wasn't done on the embedding space. This was done directly through the audio files.
Yeah. But then you end up in another audio file, right? So you basically the result of this. I understood.
Yeah, I think we were a bit confused with our roles and how to combine them together. So I think this part wasn't done with that in mind.
And to make the system usable, we build an interactive GUI. User can load the dataset, filter, and select rhythm loops, adjust generation parameters, and immediately listen to the generated result. The GUI is decoupled from the backend, so different generation methods can be easily integrated without modifying the interface. And here's the live GUI demo. Okay, so the screen here is our GUI application. We have several columns. First, okay, so the screen here is our GUI application. We have several columns. First, here's a place that we can insert our data set, which already processed by our notebook, which is the text 1 to text 4. We will have this GUI metadata for our loading in this website, and also we have a wave file which we can choose our target loops. And here we use a search system, which based on the filter, we can choose the range, the BPM we want, and the candidate loops will change, which is filtered. And also, we can use some keywords to search the loop we want. For example, if we want to try the loops with the drum, we type drum. And the candidate loops here, which include all the condition we need, which is the range of this BPM and also the drums. Okay. After using this search function, we can choose some loops here. For example, if we randomly choose 3 loops, which have the same BPM, now we can change our generation parameters, which we have the output, which we can decide how many WAV file we need, and also the creativity. From 0, which is more conservative, and from to 1, which we will have a more random generation wave in our system. And also there's a random speed and the target sample rate, which I will set default usually. And finally, here's a target loop length. For a more stable sample, I will choose from 1 second to 4 seconds. 1 second to 5 seconds, so now I choose 4 seconds. And then we can plot the generate. And now we can have a 2 generated WAV file. And we can open our file to see the output. And we can see here is our WAV file we need.
Okay.
And for how we generate the system, And for how we generate the system, I use the
Okay.
I don't know. The video has stopped.
Oh, it's okay. It's okay because I think I understood. I think I got it.
Yeah, I think there was some echo in the video.
Yeah, yeah, exactly. Because I tried to mute you to see if it was the echo from your side, but no.
Yeah.
Okay.
So
I understand.
unfortunately, the rest of my group isn't here, so I can't really help with answering.
No problem. No problem. But this part is clear. This part is more clear. Your part was the more interesting one. Yeah.
Yeah. So that's it for Group C. Thank you, and have a nice day.
Very good. Very good. Okay. Okay, let's go to Group D. And we have a Group D, right? Yeah. Group D and Group E. Okay, Group D. No? Group D. Group D, you guys are here?
Yeah.
Hello. Whenever you're ready, guys. Guys, while you're here, please make sure to answer to the forms in the chat, because by Friday we have to submit the grades. So please help us. Yeah, go ahead.
Okay, so we are Group D, and here is our member, and this is our final challenge. Next page. So this project focuses on the Freesound Loop Dataset, and our main goal is to build a system that allows users to generate new audio loops based on their preference through a graphical user interface. But I have to mention a thing here. So one of our group members whose job is the interface part. So a week ago, one of his family passed away, so he can't do any part of his job. So we only finished 3 tasks.
Listen to me. If there is something personal that happened to the student, you know what I mean? You should not reveal this personal information to me. Meaning that if you tell me, oh, the student couldn't do it because of personal reason, that's enough. I'm not gonna go and ask you, oh, is it really a valid reason or not? You know what I mean? It's like,
I know.
You should not feel that you know this is people's lives. It doesn't. What we're doing here doesn't matter, right? Meaning that don't feel that you have to justify these things by revealing personally. Just say, oh, he couldn't do it for his own reasons. I'm not gonna go and penalize you guys, or you know, it's you understand what I mean. I don't want you guys to feel that you have to disclose this type of personal information, which is much more important
Okay.
for your life than taking a course with me, right? So please just say, oh, he didn't do it, he couldn't do it. No, I'm not gonna ask you anything else. Go ahead.
So instead of directly synthesizing audio from scratch, we aim to recombine and select existing loops in a meaningful way and guide by learned representation of audio content. So to achieve this, the overall pipeline is divided into several tasks. First, we pre-process the raw data, then we obtain embedding that capture the semantic characteristic of each loop. And these embeddings are later used for clustering, selection, and generation, and the selected loop are finally passed to the downstream audio generate. Next page. So the first task is embedding. So in task 1, our focus is on generating embedding for the audio loops. After a quick processing step, we found that some metadata in type entries were missing, so those samples were dropped to ensure data consistency. And for the remaining audio files, we standardized the format by converting all loops to mono and resampling them to 16 kHz and trim to padding them to fixed length for 4 seconds. And this sample link rate is chosen because the VGG model converts a frequency range from approximately 125 to 7,500 Hz, which is sufficient for most musical content in the dataset. And we then feed the processed audio into a pre-trained VGG model, and the model outputs a 128-dimensional embedding for each loop, which serves as a compact representation of the semantic and content of the input audio. And this embedding form the foundation for our sequence tests in our systems.
Yeah, so the same discussion that we had before. Let me just calculate a second the compression rate that you have here, right? So the input samples are can you tell me how many input samples? You should still be around 10,000, right?
Around 10,000. Here is the loop ID, like 10,900 probably.
Got it. Yeah. So your compression rate is still okay. Very good. Very good. Okay, go ahead.
Okay, next page. So why we choose VGG? The mainly reason are two. So first, the embedding produced by VGG are semantically compact, and this means the model is able to encode meaningful patterns such as texture, general sound characteristics, something like that, and into a relative small vector. As a result, downstream models do not need to be very deep or complex to work effectively with this representation. Second, VGG provides a much lower dimensional representation compared to raw audio or spectrogram inputs. Each loop is represented by 128-dimensional vectors, which significantly reduces computational cost and makes clustering and density model more practical. Additionally, although VGG is a general-purpose audio embedding model, its way of organized sounds align well with our goal of matching musical styles and genre, making it a suitable choice for this task. Next page.
Agreed. Wow.
Okay, this slide shows the work of me and it's focused on clustering in the embedding space. Before we generate new audio loops, we first need to select suitable existing loop as a starting point. So our goal is to find a coherent group of audio loops. Our method is very simple and step-by-step. First, we choose a J row and a BPM range. In this example, we select rhythmic loop with BPM between 120 and 140. This helps us narrow down the data and focus on loop with similar rhythm and tempo. Next, each audio loop is yes. Each audio loop is represented as a BGG embedding because the embedding is high dimensional. So we use PCA to project it into 2D space for visualization. In the PCA part, the blue.
Sorry. Can I stop you there? Can we go back to the previous slide? Because so what is the loss over which you train this VGG? It was a triplet loss, right? How did you train it? The VGG, did you have just an end-to-end training, or did you have a triplet loss as well? Can you tell me what was the loss that you used in training? Yeah, which loss did you use in training the VGG?
It's a long time ago. I need to go back to the code.
Let me just check. Let me just ask you this. Did you have something like a triplet loss, contrastive loss, something like that?
Yeah, I think so.
Okay. Okay, go ahead. Yeah, please confirm it to me when you figure out, because when I see the plot, my first thought was whether you'd use triplet loss, because it seems that there is no cluster emerging. Go ahead.
Okay, and in this plot, the blue point represent all audio loops, and the orange point show that the selected cluster. And in this plot, it means these loops are
go ahead.
Similar in audio characteristic. Then we sampled a new point called Z, and inside this cluster using the Gaussian distribution. The sample point represent a new target sound and stay close to existing data distribution.
Just a second. Do you have a bigger plot of the PCA? I'm trying to put. I'm struggling to see. But can you maybe can you make this plot full screen maybe? Just make it big. Yeah.
There is a green point on it.
Yeah, now go again into full screen, please. Yeah, I think the pair is still. Now the quality of the figure is too low. Doesn't matter. Okay, go ahead.
Okay, and finally we apply KNN and reserve the top similar audio loops to this sampled point.
Just a second. So you said that you do a modeling with the Gaussian random variable, right? But for the Gaussian modeling, you have to choose like what input do you put to the modeling of the Gaussian variable?
All data and choose the top 10.
So this is a multivariate Gaussian, right? So it's a multivariate Gaussian of dimension 64, correct?
Oh.
Right? Okay, good.
Okay, next page. This slide showed how we check the quality of our sample point and the selected loop. On the left, we perform a sanity check. We measure the distance between each loop in the cluster and the cluster center. We compare it with the distance of the sampled point Z. The vertical line shows Z. Because Z lie within the main distribution, we know that it's not an outlier and stay close to the desired cluster. And on the right, we show the KN distance curve. This distance of the nearest neighbor increasing smoothly, which means the selected loops are consistently similar. This property is important because similar distance usually lead to more stable and reliable generation result. My part is over here.
Just a second. So look at the left one, right? Why isn't the mode of the distribution equal to the mean of the Gaussian? Because that should be when you do the Gaussian fitting, that should be the first thing that the Gaussian fitting attains, right? That the average distance is equal to the mean, right? So why is it not the same? Why is it not centered there? You
You
understand
mean that
you understand? Go ahead.
you mean that the z new point isn't in the mean of the sample?
Yeah, so the distribution of the z when you do the sample.
Maybe because we choose a new z, and it the best similar to the original data, but it's a new one.
Okay. Yeah, it's also the fact that this is a positive defined distribution, right? So I think I know what happens. So what happens is that take the distance and do not put the square, right? Then the distance can be both positive and negative. Take the difference and don't put the distance. Then this distribution will be a smooth distribution around the mean. Then when you put the square flips the negative part of the distance back to the positive part. And the contribution of the tail is what gives you a peak here. That's my suspicion.
Okay, thank you.
Go ahead.
Okay, next page, please. Okay, so in this part, we are trying to generate a new loop. So after that, we have a top 10 loop from the previous work, and then we're trying to regenerate it into the new form of a new work. Okay, just go to the next page, please. Okay, so what we do is first, because we have a range of the BPM, so we first need to find which BPM we want. So the way how I do is just try to take the mean value of it. So it's 130, which is 130 is our target BPM. And then for the sorry, for the next step we do is I do the way how I do is AB, which is the first beat. I use the top one of the loop, and the second beat I use the second beat of the loop, and then this was what is A and what is B, and we do AB and AB, and then what we do is we make it fade out and fade in between each loop when we are changing, or otherwise there will be a clicking or the clipping sound in there. So there was a 10 microsecond fade out between every loop. And then last, what we do is I repeat this process 4 times. So it has a similar length to the original data, and regulating the volume to preventing any spike inside of it. And can you please play the
Sorry, but what about the embedding? You didn't use the embedding for this? You didn't use the embedding?
What's embedding?
Yeah, the VGG, the 64-dimensional vector. Didn't you use that one there?
No,
But then why did you use this point then?
Sorry,
can So this you're just manipulating the files. So there is nothing that is being generated. Because the idea is that you do the sampling on the embedding space, and then you do the invertible transformation. You obtain something on the audible state. Basically, if you do this transformation on the embedding space and then you invert it later, then you get something more interesting than if you just do it in the time domain, right? So these are just time domain operation, correct?
Right.
Not interesting, right? Not interesting. Like why did you do all the previous part of the challenge if you're not going to use the embedding? Why? You know what I mean?
Yes.
The idea if you do the transformation in the embedding space, and then you bring it back to the original space, then you get something interesting. This is not particularly compelling. You know what I mean? You didn't use any of the previous part of the challenge.
Yeah, I understand, because I actually do the 2 version of it, and the first version I have using the embedding stuff. But
okay, so just show me the one where you use them. Yeah, just show me the one where you use them.
However, the result is just sound like identical to the original loop. So there, I didn't hear any difference between the loops. So I do this.
Wait a second. So you take you take how many loops do you have here? 2 loops. How many loops do you have? two loops.
You mean
right?
like in this version or the
Yeah, in this version you have two loops, correct?
Yeah, right.
So you take the same thing, then you have the embedding of the first loop, the embedding of the second loop. Then you choose a point in between in the embedding space, right? That's the point in between that you choose between the alpha. The alpha decides how close you are to loop 1 versus how close you are to loop 2. Then you add the invertible transformation, and you're back in the audio space. And then, of course, you have something which is different, right?
Oh, right.
But you understand what I mean? This part is not interesting for me. You could have done this the first day of the you could have done this the first day of the class, not the last day, right? Like what did you learn from the whole class that went into this part? Nothing, right? Okay. So why would I put it in the final challenge if there was no challenge? Okay, no problem. Go ahead.
Okay, so that is what I've done in this part, and the next page, Jan. Oh, so please play some loop, please. The loop. Please. Hello.
Yeah.
Yeah, we have only finished the final challenge to task 3, as I just mentioned at the beginning. So this task 4 part, he can attend this class.
Okay, right. Okay, good. No problem.
So this is about the GUI part, and we didn't make this one.
No problem.
Okay, so we can play some video sounds we finish in task 3.
Very good. Go ahead.
杨主任，你可以播吗？
可以播。
Okay, I'll do it. Wait me a second. Here's my. Okay, I got it.
You did everything almost right, guys. Why did you screw up the last part? You had everything. And then the last part, you just did some time interpolation. Come on, guys.
So this was the original way, which I do.
But this one here, you have to open it in a Chrome tab if you want to share it.
Huh? Sorry, how?
I mean, it's because when you have to open it in the Chrome tab and then share the tab.
Wait, how do I?
I don't know. It's your computer. I don't ask you on my computer.
我建议你可以帮我用一下，因为我东西已经传到 Line 上面了。
我试试看。
You have to put it in the present. I don't know. You have to put it in a presentation somewhere, and then you share the presentation. Then you play from the presentation. So, by the way, the guy that was checking, did you use the triplet loss, right, for training the VGG like stuff? The student never answered to me.
Yeah, I go check the code. I didn't use triplet. And
that's why the embedding was. That's why. See, because the lady that presented the embedding, you can see that there was no clustering in the embedding because you didn't use triplet loss. So if you don't enforce if you don't enforce triplet loss, then the geometry of the embedding space is does not reflect anything interesting. Doesn't have anything interesting. So maybe that's why also when you were trying with task 3. Since you didn't have the right embedding, then
okay. So
why didn't you use the embedding that I suggested? I suggested a pre-trained embedding, right? Why didn't you use the embedding?
I thought I could just use the VGG to.
I mean, you could, but you could, but then you know what I mean. But then there were some subtleties. I mean, there were some aspects of the problem that were not clear to you, right?
Okay.
Did you read the paper corresponding to the model that I suggested?
I only read some of them.
Yeah, because they talk about triplet loss and yeah.
I'll just play the sound through the microphone. I hope it works. So this one is the original wave. Are you able to?
Yeah, we cannot hear. Don't worry. It's okay. It's okay. You can post it on Slack, and then we listen to it on Slack.
Okay.
Very good, guys. Do we have a group E? I forgot in all my age if we have a group E or not. We should have a group E, right?
Yes, we have a group E. Yes.
Okay, go ahead.
Give me one moment to share the presentation. I have to say, I did this project totally on my own, as I'm with Singaporeans in a group, and they have now work and study, and they didn't react anymore. So I did this one on my own. And I was quite in a hurry, as I'm as well working in Holland now full time, so I had to find some time besides the general schedule. But let's start. The final project.
Singaporeans, the semester was not over, or they just got busy with their internship. Do you know what was the problem?
Sorry, what did you say?
So why did they go offline? Because they had internship, or because they went back to school, or?
We have internship starting last week.
I think they have internship and school, but it was like a combination. Not everyone had the same thing. So,
but you guys still you guys are still a strong group, right? You guys still have a good relationship with your teammate. You understood that their struggle.
Okay. Yes, it was fine, but it was a bit a problem, as we had some time difference as well, 7 hours time difference, I think. So the communication was, when the module finished, it was quite hard, and it was hard to finish the project.
Tell me about collaborating between Europe and Asia. Yeah, tell me about it. Go ahead.
Thank you. Let's start with the introduction. We did first some data preparation. The goal of our project was to build and explore audio domain music generation by making a system that creates loops based on rhythm, which is made on a style cluster defined by user input. For this, we made use of PCA for embeddings and Gaussian mixture models for sampling. We brought this together in a GUI dashboard. It was we have used Google Colab to do this, as it was more simple and it was more easy to do it that way. For the pre-processing of the data, we used the dataset varied in duration and sample rate to ensure consistent input factor. We standardized all audio to the following values. Sample rate was 22,050 Hertz. It's more general. And the duration was fixed at 4 seconds. This made the dataset uniform, which is a must for PCA. Let's move on to the second one and to the embeddings task 1 and 2. For this part, we had an encoder part and a decoder part. In the encoder part, we made use of short-time Fourier transform to convert waveforms into spectrograms. This is better readable. This time frequency representation works better to represent the harmonic and rhythmic content better than purely raw data. The spectrograms were normalized and passed through a principal component analysis (PCA) model. We made use of a latent dimension of 64, as like this is normal. We assumed what we have learned in the past, which captures the most significant variance while discarding noise. Then the encoder part was put into a decoder part to make it music again. We made use of a decoder to generate the audio. We inverted the PCA transform to recover the magnitude spectrogram. Since the phase information was discarded during the STFT step, we made use of an algorithm, the Graphene lim algorithm, to estimate the phase and to reconstruct the time domain waveform.
Let me stop you there. Lots of things here. It's lots of good things because you did this basically without a deep architecture, right? So when you do PCA, you do the compression from whatever 1,000 documents down to 1, and then you do a zoom inverse for the decoder, correct?
Yes.
Correct. So tell me, why did you use only the magnitude spectrum? What prevented you from just using the complex version of PCA?
Mainly time.
I'm not going to argue with you. Go ahead.
Yes. Then we move on to the machine learning model. To generate new loops instead of reproducing already existing loops, we implemented a density estimation method. The user can select some loops in the GUI dashboard. These loops will form a style cluster in the latent space. Then we fit a Gaussian mixture model, GMM model, to the embeddings of the selected loops. This creates a probability distribution which holds as a place for a selected style. Lastly, by drawing a random factor from the GMM, we obtain a new latent point that is mathematically similar to the inputs but sounds different. We furthermore added a creativity factor. This scales the covariance matrix. If it has low creativity, the samples are near the mean. And with high creativity, the samples are in the tails and far from the mean. So there's lots of difference. Now we move on to the dashboard. I put it over here, but I have it as well in the Google Colab. As you see, it's a quite simple dashboard. But the dashboard is implemented in Google Colab itself. The interface makes use of the EP widgets to provide a nice dashboard overview. When you press the control button, you can select more files as input files, and then music, and it will generate a nice beat. Let's move on to the results. The results in conclusion. Regarding the audio quality, it generates coherent audio loops. The PCA embedding captures the rhythm well. However, the Graphene lim algorithm and the decoder leads sometimes to a bit of noise in the music, as it's not that fluent. I'm still not Armin van Buuren or someone else, so there are still improvements to make. The style transfer is sometimes good in the music. However, it shows in some mix a really weird transfer. As long as you combine similar loops, the result is pretty good. As you can see over here, there are I think 60 input files, as it took ages in first instance to input the file, so I made it a bit smaller. You can select files that are like a blue point, and then it will select a random point which is generated with all the dimensions, like rhythm or tone, that are all possibilities for dimensions, and it will generate music. To conclude, we successfully implement a rhythm loop generator system that meets the requirements by combining both classical signal processing with machine learning. We created the tool and dashboard that allows users to use unusable latent space. This was our presentation. Thank you for listening. I will let you hear some music.
Great. Very great.
Give me one moment. Let's see.
So you have to do the same trick. You have to put it in a Google Chrome tab somehow.
Yeah, I have to wait. I will share the Google Colab.
Yeah, Google Colab will work.
Like or you can select other music files like free. I mostly. Hopefully it will now be good as well. Like, and you see it as well, like in the generated waveform, there is some rhythm and it looks logical. Did you hear the music, by the way?
Just give me a second. So for this phase recovery algorithm, what do you put in the phase recovery algorithm? Do you remember?
Yes, I did put the phase recovery algorithm.
Yeah, but what does the algorithm take in? Like, I don't know that algorithm. What does it take in as an input? What does it produce as an output?
It was, I think, a standardized function, and I got it together with Gemini AI. But it was like it is a function, and it takes as input. I will look in the collab.
I see. Because the results are really good. The results are really good. And this
yes,
is only
it's
only with PCA.
It is sometimes.
Yeah. He was so busy, he didn't even change the name of the file, Untitled 4. You know, he was so busy.
I still have to do it.
Gaussian mixtures there, array, maybe plus covariance, so you add the covariance there. Short time Fourier transform.
I think the embedding is done.
Inverse transform, that's good. Griffin, there. Stay there. He's there.
Yeah.
Librosa Griffin Lin. Okay, let me check the references. Can while I do that, can you show us can you make us listen to each loop by himself and then the mixed loop? Can you do that?
Sorry, what do you mean?
Can you? So you just made us listen to
the Gaussian mixture. I see it over there. Yeah.
No. I want to hear loop 1, loop 2, and then the mixture of the two.
Yes. Yeah. I will. This one. It gives an error if I only choose one loop.
No, yeah, I really want to hear it. Yeah, because I want to see how close it is to one or to the other, and then it gets further and further away.
I have as well selected sometimes at the beginning. I selected 10 loops as I thought the challenge was to select 10 loops and then make an audio output, but it was like 10 different audio outputs. However, if you select 10 loops, it is getting really noisy. Then like it is going great till 4 different music loops. However, if you put more music loops, it's getting getting some noise.
But do you know, like intuitive? You have a sense of how close it is to the original loops with this Creativity 2.7? Does it really stray far away, or do you know?
It is a bit further away, and but it's still quite close. But I can't exactly say how much. You have to Google like the numbers, the point, WAV, the wave, like the music in your folder.
No, because it's nice. It's nice. The results are very natural. The results. And I wonder, because you just did PCA, which is a very simple, is a much simpler approach than everybody else that did the deep learning approach. I wonder.
Mm-hmm.
Oh, it's very good. It's very good. Huh?
Thank you.
I think we can start a career. You know, it's and there is a lot of deals that made Spotify with AI artists. I think we can have also like a.
It was quite fun to do. Like it was in first place a bit difficult, and like with numbers, it's more logical, or it makes more sense to me. It's like when you hear you are going to make music, it sounds really difficult, at least, but it's like the same principle, so it's quite fun.
So what you're saying is that the other challenges that I gave you, they were not fun. Is that what you're implying?
No, initially I preferred the other challenges. That's what I'm trying to say.
So you say that I gave you the opportunity to explore something that you wouldn't have done without your beloved professor. Very good.
Yes.
Okay, very good. Anything else, guys? Otherwise, I think we are done for today. Thank you, everybody, for being on time. We're good on time. I see that some of you got confused on the challenge. Remember that you can always come and ask questions. And in fact, in the previous weeks, I was always there during the class slot. So if you had some question, you could come and ask. Please, let's do the following things. Right now, just go and fill in the forms for the evaluation right away, because we have to give the grades by Friday. And we want everybody to be available to be able to grade. Second, next semester I'm teaching 2 classes. One is the deep learning one. The other one is the numerical recipes for machine learning. You know the drill. You know the material. It's all interesting. It's all an evolution of the material that we saw in this semester. So it's very natural for you to take the class. You know how the class will be. So I think if you like this class, and especially in terms of the organization, also take it the next semester. What else? If you want to discuss any research, any plan, graduate school, recommendation letters, how to make money in life, how to find love and happiness, just let me know. I'm always available. And otherwise, I guess this is the end of the class for this semester. I'll see you all next semester in my other classes. And I'm going to mute myself, stop the recording. If you want to say something else, share something else, just let me know and we'll discuss that, okay? Ciao to the guys on YouTube.
Ciao, ciao.
Ciao, 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 ciao.